Okay, good morning. We'll get started. Okay, so homework 3 will be posted today, hopefully by this morning, and it will be due on the 17th, so in 2 weeks, as usual on Friday. Today, we'll talk about how we can extend linear regression to polynomial regression. Talk about that. And then looking back at the normal equations and the problem with normal equations, right? And we'll start to look at how can we solve using gradient descent. And then we just introduce a little bit about the Newton's methods, and we'll talk about Newton's method next time. Okay, so our exam is coming up in less than 2 weeks, on the 15th of February. It's a Wednesday. It's a mistake to make it on Wednesday. I think I was planning on Friday, but that's fine. It's a Wednesday, so we'll can slow down a little bit. It will be online. You will have a 12-hour window to take the exam. Between 8:00 in the morning to 8 p.m. at night. The students in the UF section, the distance learner students, will have until the weekend to do that. It's so far, it's 1 hour and a half roughly exam. I added 15 minutes just in case, but I may add another half an hour, depends on how it will look like by Friday. If I feel that you need more time. So this will include everything. I'm still not sure if I'm going to do it on Canvas or do it on Datescope. I have it in both formats. I will decide basically by the end of the week. Any question about the exam? Yes.
Is it open to
Everything.
you can Google, you can look at that or
As far as I don't speak to other human beings, right? Or chat to be Yeah, I mean, as far as I don't speak to other human being, then it's fine. So the materials, the first 7 lectures. So linear regression is part of the exam. Today's lecture is not part of the exam. Okay. So polynomial regression is not, linear regression is part of the exam. Okay, so mainly classification and linear regression. Any questions?
do we have to upload some written copy?
What's that?
Do we have to write and upload something or
Yes, in either way, either in Datescope or in Canvas, you will have to scan your paper and upload. Either I'm going to use it for grading or use it for regrading if you ask to regrade some parts. Okay. So I will add, so that's the 15 minutes I added. Is really kind of just to scan and upload or your iPad or whatever. Just to upload a PDF. Any other question? Coding, I mean, do not be like coding like in the homework. I mean, that's what we do most of the coding. There will be a question about coding, but things that are not, buggy. So you don't have to be bugged a lot. But you need to, you don't want to, if you didn't do the homework, then you'll spend maybe 15, 20 minutes on the coding problem. If you did the homework, then it should not take more than 2 minutes. Okay, for the coding problems. Because you build the functions, right? Any questions? Are we good? An exam? Clarified now? Okay, good. All right. And I will be available on Piazza. We will have Salim and I, but mostly myself, I will be available on Piazza real time, those 12 hours, just in case there is an issue, especially the first 2-3 hours when people take the exam. If anybody has any question, especially logistically, then I will be there. But we will have very clear instructions. By next Monday, I will go through the instruction page, which is a full page. The homework is your best sample test. I mean, it's the reason you spend 10, 15, 20 hours in the homework. That's the best sample test. Okay. Okay. So let's look at what we have done last time. This is linear regression. This is the equation, right? So we brought everything into the table. How we did that? Basically, for our vector for the sample I, for our data sample, we entered 1 here. For capital X, our data sample matrix, we put each row in one sample, we added a column of 1, right? So this basically, I need to speak into the microphone. So basically, we did this last time to really bring everything into just one format. So we have the columns of 1 in the capital X, that's our data sample. And then after that, each row is one sample, right? And then each sample is represented using capital P features. And then we have our theta or theta hat, that's our parameter, our model parameters, right? These are the weights, starting with the bias theta 0 all the way to theta P, where we have one weight for every single feature for our data samples. And then between the y hat, our prediction or our estimate, and the y, we have basically a residual error, right? An epsilon in here. And we are trying to minimize this error. So what were assumptions we did last time? Basically, we started with the Bayes rule. I remember that. And then our assumption that we are really drawing these samples from a Gaussian distribution, right? And the other assumption that these samples are independent of each other, right? Once we did that, then we set up the problem to look something like this, where our Gaussian, basically the mean value is our theta times xi, right? And then we have the standard deviation or the variance sigma square. You can really choose it to be just a one or a constant, so it doesn't make a big difference. And then, as always, and you will see that in homework 3, we really work with the log, and then we multiply by a negative one. So we are, instead of maximizing the likelihood, we are really minimizing the negative log likelihood, right? So this becomes basically our optimal function. And then it turned out to be basically nothing but really a least square problem, right? And this is the estimate, this is the ground truth, the difference, square, and then average over all our samples. And then we took the derivatives of these with respect to the thetas, and then we came up with normal equations. Basically, this is the solution, right? Solution here. If you are given a training set, we have the ground truth in Y, we have the data samples in X. Now we can really have an estimate of what the thetas will look like. So we have a closed form solutions in here, okay? So now basically that's what we did last time. Okay, so now in general, we have this, we don't really have that linear relationship in our feature space. So imagine that we have a single feature. So we have the x1 on the x-axis. We have our y, that's basically the output or the prediction or the ground truth in this case on the y-axis. And you can see in here to fit this with a line is really not very clever, right? So basically, you are having quite a bit of an error here. You are really missing out quite a bit of the relationship between y and the input features, right? So this is in here is very obvious from the data just by looking at it. It's a linear relationship. However, our linear regression is linear, right? That's the whole model that we have done so far. Remember, in the MLP and the CNN later on, we have our activation function where we put nonlinearity, right? After each neuron. But now we don't have that in the regression. Yeah, not yet, right? Okay, so how do you do that? And if you remember, I mentioned this in the SVM lecture, where we said, okay, if we have such a situation, then we rely on kernels, right? We bring a kernel into the picture. This is a kernel basically is an operator on the X, an operator on the features, and an operator on the sample of the data that we have in our input data. So now, the same thing, we really use the kernels to impose this linearity into the feature space in here. If we do that, then our model becomes something like this. So we have yi, that's basically the output prediction for sample I, is equal to the bias plus the weight times now, instead of really multiplying the weight times xi directly, where xi is a vector for sample I, a vector of all the features, we just basically take the kernel of that sample. So we have phi of xi in this case. Okay, so we have a linear function in here. Now, if we have, we can have really a more, so if you look in here, what's already the, if we are looking at, this is a simple linear function or a single function, but usually our data have much more complexity in them. Like you have a sinusoid, for example. So you want to have more than just a single kernel, right? So what we do, we can really, again, we are looking at a single data sample xi. So now we are looking in here, the first weight is multiplied by the first nonlinear function, phi1. The second weight multiplied by the second phi function. But look at each one of these functions have the same data input, right? So now what we are really trying to do is we are trying to model a much more complex nonlinear model using multiple phi functions in here, or multiple nonlinear functions, phi1, phi2, all the way to phi m. What you can see in here, the degree, how many of these phi functions we have m. So we're really imposing another another parameter in here. So we have capital M, this is the number of samples. Capital P is the number of features. And then now the small m is basically how many of those nonlinear functions we can really use in our model, right? So in this case, we have m of them, right? And we're not really imposing anything for our, so phi 0, it's kind of as a 1. Phi 0 is just a 1 in this case. Okay, so now where our transformation is basically happening using these phi functions. So we can rewrite this, basically this model in here as follows. So we have what the yi as a vector, right? Is an output. And then we have the phi transpose. Basically, this is phi in here are still the weights. So we have phi 0, theta. Theta 0, theta 1, theta 2. This is in the theta transpose vector. And then, once you log in, just let me know so I can mute my mic. And then we have the phi functions in here. So this phi is starts with a 1 as we did before. And then we have phi 1 of xi all the way to phi m of xi. So you can see the modeling that we are really doing in this case. Okay. So now what we are really hoping for is that if you have the data on the left-hand side, that we will be able to basically model it using this red function, right? So this actually makes much more sense than the linear function or model that we had before, which are one line, right? That's basically what we're trying to do. If you look at the data in here, we generated this data using this quadratic equation, right? So we have ax squared plus bx plus c. So we expect basically our model, right? You can really just look at it. We will be very successful, right? If basically we can really mimic what we have in the original data that generated, right? If you can really have the first basically function, right? If you look at the first function, p1 of xi, if we can do that as xi squared, right? That could be one function, right? So basically that's phi1. Like phi1 is basically squaring the input data. And then theta 1 will be the a, right? And then what about phi2? Phi2 will be basically nothing but just multiply, it's just x by 1, right? So there's nothing really to do with that modeling. And then theta 2 will be a b, and then with theta 0 is our c, right? If we really model it that way, then actually in this case we have very successfully modeled the data. Do you see that? What we could do with the polynomial? Yeah. Can I mute myself now? Oh, sure. Yeah, just let me know. Okay. So now let's really look at the case study. Right? The first one, let's really just assume that we have a single feature, right? We have every sample, every xi has a single feature. That means capital P is equal to 1, right? Just one feature per sample, right? And now we'd like to really have the polynomial, right? So now our phi1, phi2, phi3, phi4, nothing but it becomes basically a polynomial order. So if that's the case, then our prediction or our model of what yi will look like, we have the theta 0, the bias, right? Plus theta 1 times xi, right? That's basically the feature as it is. Basically, we're just scaling the feature. The next one will be theta 2 times the feature square, and then all the way to theta m times xi to the power m. So now we have imposed a polynomial with degree what? Small m. So now we translated this function or this model in here, where we just say basically our theta, our phi modeling is nothing but a polynomial, and then small m is the order of the polynomial, the highest order in the polynomial. So in this case, basically we can really model this using this equation. Again, remember that every single sample has only a single feature in this case, right? And you can imagine that, I will see an example. Once you have more features, this becomes very, very complex, right? This becomes really a very, very complicated model. So now our outputs, basically we have them into a single vector y. So this is the first prediction for the first sample, the second prediction for the second sample, and so on. And then we have our phi of x. This is basically our linear model function. So we have phi of x1. That's basically the model for the first sample. Same thing for the second sample. But you can see we are using the same model, right? So we have the same model for all the samples in here. Now, what is the model? We have one, as we did before. And then the next one is our theta1 multiplied by x1. Remember, theta1. And then theta2. Should I mute myself now? I see you. Okay, so remember, basically we have the same operator for all the samples. So in this case, we have 1 times theta0, then x1 times theta1, x1 squared times theta2, all the way to the mth order, which is basically x1 to the power m times theta m in this case. And now we have basically our error. So we can rewrite our model in this case using this equation. Any question about this model in here? Yes. Exactly. So basically, the question is the m in here. Is it the number of weights? It's working? Okay. So basically, the question is, are these the weights? Remember, our model starts with basically as a single feature, right? We first specify what is the polynomial degree, right? So m is basically by designing what if we have some knowledge about where the data is coming from, then we say, okay, I would like to use a polynomial of degree 3 or 4, right? And then once I specify that, then I specify what is the weight vector, right? So the m is really coming from my polynomial, definition of polynomial setup or polynomial design, right? And then the weights in this specific example, then the weights will follow through, right? But really it's important to think about the m coming from the polynomial, not from the weights, right? Because before the weights were associated with the features, like the number of features, right? I have, but now I have another factor, which is the polynomial, right? Degree. Okay. So once we have this model here, then basically everything else will just follow through as we did before. So now let's really complicate this a little bit further. Let's really say we have the same setup. We'd like to use a polynomial, but now our polynomial of degree 2. But at the same time, our data samples have 2 features, not a single feature. So each x1 has x11 and x12, right? So I have 2 features for the pairs x1. And then the same thing for the second sample. I have x21 and x22. Third sample, I have 2 features, x31, x32, and so on. So now I could really specify basically a polynomial, right, of with these 2 features as follows. So I have the bias theta0 as it is, and then I have, as if I don't really have a polynomial, right, then I will have theta1 for x1, right, for the first feature, and then theta2 for the second feature. I stop here, right? That's our linear regression model, right? That's basically I have 1 weight for each one of those features, correct? I stop here, right? That's what we did on Wednesday. Yes. Why I don't have an m in here? Yeah, so the question is why don't I have m? This is a very specific case where I m equal to a2, right? So that's the highest degree in the polynomial, right? So I have, this is, remember, these are very special cases. This one here, I have a single feature. I have a polynomial of m, right? And here I have 2 features, but here also I define m equal to a2 because I just want to showcase a specific example, okay? So now, if I do a linear regression, then I will have basically my theta0 plus theta1 times the first feature plus theta2 times the second feature. I stop, right? But now I use a polynomial, right? So now I have the next one, because I have m equal to a 2, that's my highest polynomial degree. Then I have theta3 times x1 squared. Remember, xi1 is the first feature square, but also I have the second feature. So I have theta4 times the xi2 squared, right? But I have the product between the 2, right? So I have the theta5, which is xi1 times xi2, right? The product between the 2 features in here, right? And you can imagine if I have 3 features,
then you will basically to the power 3, right? And you have the x1 times x2, x1 times x3, x2 times x3, all the combinations of the multiplications of all these features in here. And that's basically where the polynomial degree come into the play, because you are looking at basically how the joint features, basically the inner product between the two features, will really impact your model in here. You can start to really kind of look ahead and say, if my two features are truly independent of each other, then if I'm really doing this the right way, then theta 5 should be what? Should be 0, right? I mean, it should be a 0. If really the two features are really independent, I have the right training data, then I should really get, when I converge, right, my error, then theta 5 should really be very close to a 0, right? If that's the case. But we know in real life data, that is really not always the case, where the features are independent of each other. So now you are bringing this dependency into the equation. So now, again, remember, this is p equal to a 2, that's two features, m equal to a 2, that's the highest polynomial degree I have in here. Then remodel again everything as before. This is the system of equations we have. This is the output vector. This is basically the ground truth or the prediction if you add a hat to it. And then now we look at our phi functions, right? So the phi function is the same for each one of the input samples. I have n, capital N of these samples. I have start with a 1, right? Because that's 1 times theta 0, plus theta 1 times x11, plus theta 2 times x12, plus theta 3 times x1 square, plus theta 4 times x2 square, plus theta 5 times the x1 times x2. And then you do repeat the same thing for every single sample, right? So the first row for the first sample, the second row for the second sample, the last row for the nth sample. Now in this model, how many parameters do I have? Basically, I have 6 parameters, right? I have theta 0 all the way to theta 5. I have 6 parameters in this case. Any question about this specific example? Yeah.
What are the 6 parameters? Just the combination.
These are the weights. Remember, this is the weights. Always just keep this. Where is it? Keep this in mind, right? This one here, right? What's that? Why do we have 6 feet? Okay. The question is, how come we have 6 of them, right? So remember again, we have 2 features, right? Now, if I'm doing linear regression, right? So how many weights do I have? If I have, forget polynomial, right? If I have linear regression, what we did on Wednesday, then how many parameters I'm looking at? So the two, which ones? Theta 1 times the first feature, plus theta 2 times the second feature, but don't forget theta 0, right? The bias. We don't want to just pass through the origin. We want to keep it basically floating, right? So I have 3 features, right? I have 2 features. I have 3 parameters. Now I'm adding a dimension, which is polynomial regression, right? So now, exactly. So now I have polynomial function, right? So I have degree now is 2. So this is, and we'll see an example in a few minutes. I'm from a side information that I have about the data, I'm thinking maybe an order polynomial will do the job, right? So this is my hyperparameter. So I chose m to equal to a 2 in this case, right? Again, I'll show you example but in a few minutes where sometimes you overfit, sometimes you overshoot, right? Sometimes if you choose this degree to be really very high, and we'll see an example where you make things really worse, much worse, right? Or you undershoot, right? So it's going to be like within a certain level. But we'll look at that in a few minutes. But now I just, something told me that I had to make this m equal to a 2, right? In that case, if I look at all the combinations in here, for example, if this is basically the full model, if m equal to a 2 and the features equal to a 2, right? Am I required to use every single one of those weights? No, right? If I have some information tells me that basically the square of the second feature basically doesn't really contribute much, I can just basically ignore this. I don't want to have this weight. I want to simplify my model, right? If I know for a fact that they are independent of each other, feature 1, feature 2, I can remove this one, right? So, but this one here is basically the full scope, right? And I'm hoping with my training, I will figure these things out. If my weight here becomes very small, that means these are independent of each other. Yeah. so where the theta 5 coming from? Basically, all the thetas in here, they are basically as if you already have a polynomial of a second degree, right? So I have a polynomial of second degree. That means what? The square of the feature is my highest, basically, feature space now. I am transforming my feature space from having x1, x2, right? I have two features, x1, x2. I'm transforming to a polynomial feature space, right? A polynomial feature space. Now, what is the highest degree is 2, right? So remember, what we are doing, we have in the p equal to 2, I want to forget about the samples. So I have x1 and I have x2, right? So now my model, I multiply this by theta 1, multiply this by theta 2, and then I have my theta 0. I have 3 parameters. We will get there in a minute. Yes. So now this is linear, right? Now I'm doing to polynomial, but now in my polynomial I'm defining m equal to r2, right? And we'll look at the generalization. Basically, how can you expect what the number of parameters that we will use, right? Basically, it's m plus p, choose m, right? But we'll get there in a minute. So now, what are all the possible, combinations of my features with the degree of 2, right? So what do I have? I have x1, my first feature. I'm dropping the I, right, for now. I have x2, right? So I'm still using the raw features, right? The raw data. I want to use x1 square is x2 square. I want to use x1 times x2, right? All the combinations, right? Basically, x1 plus x2, square, right? That's what I'm doing. So now, that's what I'm doing, but it's really simpler than that. Okay. So now, what do I have? I have theta 1, I have theta 2, I have theta 3, I have theta 4, I have theta 5, and then I have my theta 0 for the bind. Then I have 6 features. Now, if m is to a 3, then I get to basically to the cube and so on, and all the possible combination between the two. So now I have 6 of these parameters, or 6 of these weights, right? Okay. Any question about this? Yes.
So if you would take a linear relationship with 3 through 3 and 4, I guess just go to 0.
Very, very good question. So basically, if the relationship between your data is really linear, right? And then you just model with the polynomial, then what you are really hoping for, if you had the right data, basically to train it with, then basically all the theta 3, theta 4, theta 5 will go to 0. They should go to 0.
Just 3 and 4, 5 is it?
Yeah, exactly. Yes, very good point. Yes, 3 and 4 will be 0. Theta 5 will go to 0 if they are independent, but if not, they will. Yes, absolutely. Yes. But that's why there's a big if you have the right data to train with, right? That just inspired me for a new problem. In a good way. I mean, it's not. It sounded horrible. Okay. We can repeat the same setup that we had last time, where basically we are already taking the data from Gaussian samples. Yes. Oh, sorry. Very, very good. So basically overshoot, basically just make it very complicated and see what you get. What will happen in overfitting, right? We start basically to look at, you'll start to have, because now you have quite a bit of freedom in your dynamics for the model. You'll see some example of that. And basically you start to have your model basically pass through every single data point, right? Because it has the flexibility to do that right now. But it's not really a good robust generalizable model for your data because you overfit it, right? For the data point that you have, right? Absolutely, if you do that. But if you are within a certain degree, then it will be it will work. But if you really overdo it, and we'll look at some examples in here. We'll look at some examples at the end of the lecture today. Okay, so we repeat the same process from last time, but I will not really go through the details. Basically, you sample from a Gaussian distribution again, but now you don't really look at the mean value now in your Gaussian would not be theta times xi, it will be theta times phi of xi. Now you are operating on the samples, right? So now you have the phi is in the equation. So the same thing, the cost function would have theta times phi of xi, not before we had theta times the same way. Still is a really complex quadratic in this situation, and we can solve this using the normal equation as before. Remember, what we're really doing, we just either squaring or multiplying the xi's with each other. So the same setup as before. If you take the derivative with respect to 0, then basically it will be the same as before, but now you have just functions phi of x, and then if you have x squared, then you have 2 times x and so on. So it will not really change much in the 2D. Right? So now what we will end up with basically is the same normal equation as before, right? So now if you look at more carefully what we are really looking at. So if you look at a single feature, right? So again, p is equal to a1, then phi of xi will be 1 plus xi all the way to xi m equal to a 2, then I have 1 xi squared, right? So now basically the space where the phi of xi or the data, the new space for the data is basically becoming of the order m plus 1. Now in this case, I have a single feature. I have basically my space in here for the phi of xi's is there m plus 1, right? So I went from basically a feature space of 1. That means I have theta 0 and theta 1. I have now theta 1, theta 0, theta 1, theta p if m equal to a 2, right? So normal equations will really handle the same way. So we'll solve it using normal equations, no problem there. But now look at the general case when I have p features for my sample. So the xi belong to basically space where dimension of p, capital P in this case. This is the general case in here. So now if you look at the order of the dimension of our phi of xi, basically it will be a function of the individual xi's, but to the order of p sub j, right? So b sub j in here is the power degree for our xij's in this case, right? And each one of these bj's in here is basically less than or equal to the m, right? So if m is equal to 3, then b sub j basically will be it will be 0, 1, 2, and 3, right? If m equal to a 2, then I have the order in here, the exponent will be 0 and 1 and 2, for example, and so on. So now if you look at the space, basically we are already picking the data from, it will be p plus m, choose m, right? This is p plus m, choose m in here. So those are the total number of combinations I have in this case. Again, this is the product of these, right? And we saw that in example in this case in here, right? Where p equal to a 2 and m equal to a 2, that basically means I have up to the square of the single features. So in that case, I have 2 plus 2 choose 2, right? That's 4 choose 2. Then I have basically 6 of them in this case. Okay. So I have a third degree polynomial regression in this case, right? So now this general rule tells me how many coefficients do I have, or what dimension basically our new data is coming from, which space. That will be basically equal to 3 plus 2, choose 3, right? So this is m is equal to 3. The capital P is 2 in this case. That's 5, choose m, which is 3 in this case, right? So what I have in here, I have 1 for theta 0. I have x1, the first feature, second feature. Now I have the product of these two features, the square of the first feature, the square of the second feature, the square of the first times the x2, x1 times the square of the second feature, and then x1 cubed by x2 cubed. So I have how many of them I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 coefficients. That's 5 choose 3, right? You see that? 5 choose 3 will be 20 divided by 2, that will be 10, right? So this will be 10, right? So now I have 10 parameters. I went from having, by just going from m equal to a 2, where I have 6 features, to m equal to 3. Now I have 10 thetas, right? I have 10 these parameters or weights. You see that? And so on. And you keep doing basically that. But now you start to think about, okay, now there is a processing cost, there is a a computation cost that I have to pay. So I really don't just overshoot, right? I don't want to just choose capital P or capital M or small m to be anything, right? As that is possible. Let's look at some example in more detail. So now remember the kernel where we have phi transpose times phi, right? So now what we are really doing in the normal equations, right? Remember the normal equations where we have x transpose times x inverse, right? So we are computing the inverse, right? So what is the dimension of the matrix with inside that inverse? It's an x transpose times x, right? So in this case, what is the dimension of our data? It's not p anymore. It's not a p times or p a matrix of p times p inverse. It's not anymore that dimension. There is an m as part of the equation. So now the order of this matrix or the dimension is p plus m choose m times p plus m choose m. So then that's our matrix, right? If you have enough data, and back to your question about basically how much I can grow my m, right? If you have a huge amount of data that's still much larger than p plus m choose m, right? Then basically we can still basically we can manage, right, in terms of computation. But this is the complexity. But what's really more important in here, if I have a huge amount of features, and usually in real data you have that, right? You have, imagine that you have 50 features for each sample, right? You have 50 of them. And if only you choose m equal to 3, my polynomial degree, basically the maximum is 3, then your matrix dimension will be of this order, 23,426, right? So imagine you have a matrix of this dimension, you want to inverse, right? The memory basically is a problem, right? Just to sort this in a memory and invert in the RAM it becomes an issue, right? That's a problem to start with. And imagine that basically will get all kinds of different difficulties doing that. So now that's when basically we have to be very conscious about how much we can really increase our M, because it all depends on the data that you have. And it's always, remember, and this is something people really forget about, that they assume that you have the data. But remember, machine learning, you have data, you have a model, right? Always these two things are there. And both of them are equally important, right? Your data is important, your model is very important. But I add to the mix the human who's doing all of this is very important too, right? I mean, either the human is the end user or basically is the one who's designing the algorithm. But the end user is really very, very important, because that's where things become very, very interesting, the interaction between the human and the machine learning. Anyway, so now if we use normal equations, right? What's the problem with normal equations? We have to do inverse. Remember the normal equation solution? We have to x transpose times x inverse, right? Now we replace the x transpose times x with what? Phi of x transpose, phi of x all transpose times phi of x all inverse, right? That becomes the issue in here. I'm looking at some faces looking at me as I'm speaking. Remember the x transpose times x in the solution that we have to have the inverse. Now I have phi of x, this whole thing transpose, phi of x, and this whole thing is inverse, right? This becomes a problem, right? Because we brought this m, small m, into the equation, right? Becomes very, very dimensional wise. We went from, in this case, basically we had 50 times 50, right? And here the dimension was a matrix of 50 times 50. And then here it became, I don't know, 23,426, 23,426, right? Huge growth, right? In dimension. That becomes a problem for our inverse. And that's basically where we go to our friend gradient descent, right? We start to look at this. We can really solve this in an iterative fashion. We can estimate the solution using gradient descent in this case. So now we move from using normal equations, because we brought this polynomial, and that this becomes an issue with dimensionality of our matrices to inverse. Now we go to the gradient descent algorithm. And again, we saw this before, gradient descent. And the classical basically example, you are here at the mountain, you want to go to the bottom of the valley, then basically all what you need to worry about where you are right now, right? You don't care about basically where the whole mountain is. Just look at your feet and see basically where the slope is going down and go that direction, right? And then do that, keep doing that. So and the classical example for, look at the classical books about gradient descent, imagine that you are standing on the mountain basically and there's foggy, so you cannot see ahead of just 2-3 feet. Or what you can do, just look at your feet, right? And then say, okay, now where is the slope going? And then I just go through that. That's exactly the gradient descent where they have the negative alpha times the gradient, right? The opposite of the direction of the gradient. We are subtracting that. So that's why we are going downward the mountain, not we are going upward the mountain, right? So that's what we are doing. And we are hoping basically a little bit every time, right? And how are we doing this? We are estimating, right? We are estimating, this is the true data in the blue, right? We are here with our initial loss, right? So we are really, all what we are doing in the gradient descent, we are estimating basically this as a line, right? Touching basically the data curve at that point. And then basically all what we are hoping for, you will basically go down this line here. And then do projection on our data. Then we get to this point. And then we are here now. We see, okay, what is the gradient is moving this way. So we go the opposite. So we subtract, we go this way. And we are hoping basically with time, we will get to the bottom of the mountain in this case. It's the same thing in here, right? If you look at the equations, nothing in here basically is really is new up to this second equation. We have the mean square error as before, right? We have the yi hat minus yi square. So it's the difference square average, but now our model for our yi hat is nothing but the x transpose times the theta, our parameters in this case. Now, if I take the derivative with respect to a single parameter, right? A single parameter in this case, then basically I have the summation. I have the 2 comes in the front, right? I have whatever inside the parentheses as it is. The derivative of this with respect to a single theta, right? That's why I have xip in here. So a single theta, right? A single parameter in this case. Now, if I line up all these partial derivatives with respect to different thetas into one vector, then basically I have the gradient vector in here. And that's the notation we have for it, the gradient vector for our cost function, the mean square error, right? So the first line here, the first row, the first element is the partial derivative of our loss function or cost function with respect to theta 0. The second part in our gradient vector in here is the partial derivative of our mean square error with respect to theta 1, all the way to our p feature in this case, right? And we can write this summation here is 2 over n as basically in vector format, the x transpose, because you have xip on the right hand side. Imagine now you will have xi1 and xi0, xi1, xi2, all the way to xip in here. And then I have in here is theta times x times theta. X is a matrix, theta is a vector, and y is a vector because I have y0, y1, y2, all the way to yn. Okay. And the gradient descent, basically, I'm going the opposite. So I'm really subtracting, right? That's what the whole gradient descent. But now I don't want to subtract as it is. I want to really control that learning rate. And we'll look at that. Like how much do I know I want to go down the mountain, right? So the gradient is basically hitting me up. Now I want to subtract. So I'm going the other direction. I'm going down the mountain. But now I want to control how much step. So now it depends on how much fog you have in the mountain. Is this basically 2 feet or 3 feet, or I want to go very aggressive. If I can see 10 feet ahead of me, right? Then I'll just go very aggressive. The learning rate will have to be higher and so on. So this alpha is the learning rate. And then now I go to the next stage. I do the same thing. I look at my feet where I'm heading, subtract, go the other direction, and then keep going that way until I get to the valley or the top or the bottom of the mountain in this case. Now we repeat the same thing, right? But now we bring the polynomial. Remember, all what we did in here, and I know this can be confusing for some. We switch from polynomial because it's very tough to solve normal equations if p is very large. And now so let's really go back to our linear regression that we did last Wednesday and solve it using gradient descent. All what we are doing in here, we're trying to solve the problem using gradient descent, right? All that's what we're doing. And remember, this cost function from last Wednesday, right? This is the mean square error from last Wednesday, right? So now basically what we are doing, we're just setting up the gradient descent equation in this case, right? Okay. So now we can do the same thing in here, but now if we have a polynomial in this case, it's the same thing. The gradient descent equation is the same. The parameter at t plus 1 equals the parameter at iteration t minus the learning rate times basically our gradient vector in this case, right? And now what's this gradient vector in here? Basically is really giving using the same equation as we had in here, right? But now we don't really have the x, we have the x, the phi of the x. This is polynomial. So phi of x all transpose, phi of x times theta minus the y, right? And now what's the dimension of basically the phi is really an n times p plus m choose m, where p is the feature, the number of features, m, small m, is the polynomial degree that we are really modeling with. How much did I lose you? Are we still around? Okay, any question? Any question about these two slides? It's a good review for the gradient descent. Yes. Oh, this one? Yeah. Yeah, so the question is basically, is this are these the steps? All what I'm showing you in here, how we can set up the gradient descent for linear regression, right? So now, what is really gradient descent is the same as before, right? We have a partial derivative with respect to the parameters, right? Each one of them. So now, where this MSE coming from? This is coming from Wednesday. In linear regression, we came with this equation here. Remember that? This is when we sample from the Gaussian, right? From the Gaussian distribution, where we have the exponent, and then we have the yi hat minus theta times x, where the mean value is theta times x. That's basically exactly what we are really doing in here. That's the model from last Wednesday for linear regression, right? And now we're saying, okay, let's really look at what we are really doing. Remember, when you have two features, right? So now you take the partial derivative with respect to each one of these features, and you see basically which one of those will get you smaller, right? Which direction you want to go to, right? So now if you are on a mountain, right, on the side of the mountain, then all what you have to do, what? You have to go basically either, you have 3 dimensions, right? So basically, where do you go, right? So do you go the x positive, negative, or go up and down, right? So now the same thing in here. You have, when you have n dimension, you have, so p, capital P dimension. Then you want to figure out in which direction I really want to go, right? In which direction I want to go, right? So now you have to take the partial derivative with respect to each one of those axes or dimensions. What are these dimensions? They are defined by our parameters, theta 0, theta 1, or to theta p, right? So all what you could do is basically take the partial derivative with respect to each one of them, right? And then now you have this gradient vector, right? Right? That's what you have in here, right? This is the gradient. This is what is telling you basically where you are really heading. And then you just multiply that by the learning rate. You subtract that from your thetas from the previous round. And then basically you are hoping that this basically in here will get you closer to this valley in the mountain, right? That's all what basically the setup in here. So it's really the same gradient descent as before. The only difference in here, we have a different cost function. And this cost function coming from our linear regression setup, right? This is the regression setup that we have on Wednesday. Okay, does it make sense? Yeah, okay. So now I'm adding, this is basically the first half of this, is the summary of the previous slide. And the second half is just if I have polynomial regression, what will happen? If I have polynomial regression, then I replace basically in the gradient descent, everything is the same. But now I don't really operate on the x's, I operate in the phi of x, the polynomial on the x's, right? And the reason I'm doing that, I mean, that's the whole point why I'm doing gradient descent, because the dimension of my data becomes really very multiplied, right? It's p plus m choose m in this case. Okay. And now we go back to the previous solution that we had last time. There are different ways. Remember when we talk about the epoch and the iterations. So look at this in more detail now. Okay. So now I have, these are very well defined in regression. We call them batch gradient descent, stochastic gradient descent, and mini batch gradient descent. They sound fancy, but they're really very simple because we went through this last 2 weeks ago. The first one, you calculate the gradients of the cost function over all instances at each step. Let's look at this example. So this is pseudocode on the left-hand side. So I calculate my gradient vector over the entire data set I have. That means over the entire capital N samples in this case. And only then I update my weights. You see that? So I calculate the gradients for the entire data samples, and then I update my weights. So I look at every single data I have, and then I start walking toward the valley, right? At every single step, and then I keep repeating that. The next step, I do the same thing now, new calculations on all the data, and now I update the weights, and I keep doing that. So you can imagine that at every single step, and basically we have them here, right? At every single step, this is basically kind of I have theta 0, I have theta 1, I have 2 two parameters in this case. If I do the calculation at every single step, I am converging to the solution here. This is the optimal solution I have in here, right? So you can see I'm moving from this to the next, to the next, to the next in a very smooth fashion because I'm choosing what I'm doing. I'm looking at the gradient for the entire data at every single step, right? So I'm really moving in a very steadily to the optimal solution and very smoothly, right? Now, what if I go and say, okay, now this is very expensive. If I want to do that for every single iteration I have, I do it for all the data samples I have in my data. That might be a little bit expensive. Let's look at the stochastic gradient descent, right? So that means what? I calculate the gradients of the cost function over a single random instance at each step, right? So now here is basically kind of the pseudocode. So now I have how many data samples I have? I have n of them, right? I still want to exhaust all of them, but every time I want to update my weights, I update my weights based on a single data point, right? So I choose randomly from my n samples a sample, and now I calculate the gradients, and then I update my weights based on that data sample and that gradients. And you can see now it's very basically unsteady. Right? It's far from being smooth. It's very rough optimization. I will get eventually to the optimal solution, right? To the region of very close to optimal solution, but the way there is not really as smooth as what I have in here, right? But the computation cost is much less, right? Remember, it's basically 1 over n of what I have at every single iteration of what I have in here, right? So if n is like 1 million data point, that's quite a bit of computation saving. But you get to a quasi-optimal. You may not converge exactly, but because you keep jumping around the optimal solution, eventually you will get there. But you can see basically. So now these are two extremes. This is very smooth, but it's very expensive. This is really not smooth, but it's very cheap and computation-wise. We go to the last one, which is the mini batch. This is the one basically we talked about in classification before. Now, what you do, you take your data, and this is basically the practice in real implementations. That's what you do. You take your data and then basically split it into batches, right? And you have to decide on what that batch size should look like. So if you look at the pseudocode for this one, now we take a subset, we call it x sub s, basically of size b instances at random. So now you take the size of the mini batch is the same throughout all your training, right? It's the same size, right? But now you pick basically these individual samples in your batch at each iteration in a random fashion, and then you calculate the gradients for that batch, and then you update the weights per batch, right? So now you can see in here, right? I mean, I forget to actually what was the parameter in here, but basically it's not really as rough as what we have in here, and it's not really as smooth as what we have in here. It's something in between in here, right? And we basically eventually we go to the optimal solution. Question? Yes, because you still want to go through the entire data points, all the n samples, right? And now you start to choose how much overlap you want to have between the different batches, right? Eventually, but you really want to go through, or you can just make them independent, right? But that will give you start jumping around. If you have some overlap, then you start to have smoother. Anyway, so put everything together. We have the epoch and we have the iteration. So the epoch is a sequence of repetitions which complete the processing of the entire data set. Basically, we say like how many epochs, basically each one of them, I went through the entire capital N samples I have in my data set. The iterations, if you look at it from a neural network point of view, I'm going through the whole optimization forward and backward. In this case, I'm doing the entire update in my gradient descent parameters at once, right? So that's each iteration. So in the batch gradient descent, that means I'm using the entire data set to update my weights at every single iteration. Basically, in one iteration, I'm doing that. And basically, each epoch is really complete in one iteration, right? So one epoch and one iteration, they're the same in this case, right? So in the stochastic one, I am using a single data point at every time, right? So at one iteration, I have a single data point. I calculate the gradients. I did my weights, right? So how many epochs I need, or how many iterations in one epoch I need. I need n of them because each one I'm just picking in one sample from the n samples, right? And now the mini batch in here, I'm doing a subset of these. If they are independent of each other, then I can have one epoch completes in one n over b iterations in this case. And we put them all together. Basically, you can see basically the difference. So the red one is the stochastic one, the blue one is the batch, and then the mini batch is the green one in this case. Okay. So the other parameter I want to look at is this learning rate, right? And this is an illustration, toy example. If in this case I have my x-axis the theta, the y-axis my MSE or the cost. If I choose my learning rate very small, right, then I have very slow convergence, right? I'm moving steadily but really slowly, right? If I become very aggressive and I choose my learning rate basically very high, then I start to oscillate around the solution, right? So so then my convergence becomes really questionable, right? You start to look at your learning rates, your convergence rates, and that becomes an issue in this case, right? And we talked about this before when we have sometimes we have local minima, right? If you don't have, especially if real data you don't have enough data, you will hit this local minima, right? So that's this is the issue. If you are the initialization becomes an issue. So if you start here, you will hit the global minima. If you start from here, you will hit the local minimum, not the global minimum, right? That's why basically we always iterate with different seeds, right? We have different initialization, different seeds, and that's basically a common practice. You have to have different seeds and then take the average, and hopefully that will get you to the global minima. Okay, so this is another look at, let's look at this one. The first one, I don't know which one is this. Yeah, actually there's same is batch gradient descent. So we're looking at all the data, but now we have different learning rates. So this one, this is the data we have. This is the learning rate is 0.02, and you can see basically we're really moving very slowly while getting to the true solution. If I increase to 0.1, then I'm really getting to the solution much quicker. If I'm at 0.5, which is very high actually, then I'm really overshooting in this case. I'm not converging, and so I change, and that's where. But if we refer to it as hyperparameter in this case. Again, we remember when we talked about this early in the classification, normalization is a very common practice. As the min-max normalization is for your feature before you start. So if you do it, this is how the convergence will look like. This is the iterations number with normalization. This is the cost function, the y-axis. This again the iteration, but we don't really have normalization. You are really jumping around in this case. So this really summarizes what we have learned so far. So normal equations, batch gradient descent, stochastic gradient descent, mini batch gradient descent, and then now I have performance with large N, memory space requirements, performance with a large feature vector capital P, and then do we need the normalization? The only way we don't really need normalization are normal equations, right? Because even if you do normalization, you have x transpose times x anyway, so it doesn't really matter there. Now, if I have large N, right, and small capital P, then that will still be normal equation will be really fast, right? The only downside, you have to pay for memory because your x transpose times x inverse, you need a very large, basically, very large memory for the inverse of that matrix, right? That's the downside of it, right? And we saw that if it becomes to a stage where it becomes really impossible to solve for the inverse of that x transpose times x. Okay. In the batch gradient descent, basically, if you have large number of data or samples, then basically at every single time you take the gradient with respect to everything, and then you update once, and then you keep doing that iteratively until you converge. In that case, basically, it will be slow for large N, but even the feature is really high, still is really fast, right? Because really N is really is the one that's really doing the slowdown in this case. Again, because you will have to have that gradient vector, so the requirement for for your memory still is high, right? For the stochastic one, where one sample at every single iteration, then you have is really very fast for the capital N samples, fast for the capital P samples, and then here the minimum requirement for the memory because just one sample at every time, right? The only downside in here is your convergence becomes questionable, right? And the mini batch is in between, right? So you have fast for the capital N, for large P is also still fast, and really the memory depends on how big the batch is, right? So this is basically kind of the most common practice is the mini batch example. And we kind of just look at a couple of examples before I move on. Where's my date? Yeah, this one here. Imagine I have a sinusoid, right? Let's look at this. So imagine I have a sinusoid, right? I have a sinusoid in the green, right? A sinusoid in here is linear model. So I can generate my data using a sinusoid. And now when I use linear regression to model my data, right? So now if I use linear regression, right, the degree is 1, right? That's what linear regression is. I'm not using any polynomial, right? Then I'm modeling my data and here using this line, right? You can see basically quite a bit of an error. So the mean square error in this case is 4 times 10 to the power 1, right? So that's basically kind of like around MSE is around 40 in this case, right? And really varies quite a bit between one sample and the next, right? So it's really, you can see that's not really a good model. If I do it with a degree 4, right, then I reduce my mean square error to the 10 to the power -2, right? So basically, you can see that my model in here is in the blue is almost matching. You can see there's a difference in here, but in here is really matching very well, right? Now back to the question that you guys asked before. What if my degree is 15, right? I'm having a very high degree, right? So you guys ask about this. Now I'm really overfitting. I have enough dynamic in my or freedom, degrees of freedom in my model, where I can really kind of adapt to every single data point I have in my data. I pass through every single one of them, right? I pass through every single one of these in here now. So now, if that's the case, what's really happening? Then if I have your test data, right, or you have other samples, you will have quite a bit of an error in this case. This is the error in here between my test samples and the training sample and the model, right? That's what we are showing in here. This is basically the error. So you can see this is 10 to the power 8, right? Because why? Because I fitted my model to the training data exactly. But I can't give you some samples here, there for my sinusoid, right? They're coming from the sinusoid, and the error will be very large. So this basically does an overshoot in here. You can change this. Let's see if it's this. Yeah, we can do this for. So let's make this. So yeah, let's well. Oops. Yeah. So now if I reduce this to 12, I still have the 1, the 4, and 15 as it is, but now the 12 in here, you can see the difference. This is 10 to the power 3, this one 10 to the power 8, right? Quite a bit of a drop in here. And you keep doing that. I mean, this was the hyperparameter, if I make this equal to 5, right? Let's see between a degree of 4 and degree 5. If you look in here, this is 10 to the power, is it 2? This 10 to the -2, this one -2, but this is 9.8. So this is higher. So this error in here is higher than this one here. If I go to the other side and make it 3. Yeah, this is lower, right? So the 1.8, this is 4.3. So 3 is basically my choice in here. Okay, and you can, that's a hyperparameter in this case. Any question? Okay. Yes. Oh. Can I repeat that? Sorry. Repeat that. Yeah, remember the error, this error on the testing data point, not on the training data point, right? That's in the testing error, right? And testing data point, yeah. No, that's the error in between our model and the true data. Yes, that's in our testing, right? Yeah, that's yes. Okay, so the question is the difference between normal equations and, let me go back here. Between normal equations and the gradient descent, right? Normal equation is the closed formula solution. We don't have an iteration, right? You have a closed formula solution where we have the x transpose times x all inverse, right? Basically times the y, right? Times x times the y. That's our solution. So it's a closed form solution. Just we do it in one shot. You do the inverse. You have your optimal parameters right away. If gradient descent is getting the same solution, right, or very close to the solution, the true solution, but in a very iterative fashion, right? We're using basically iteratively, right? We already minimize as if, so you imagine that you are on the mountain, right? If it's very clear, right? And you know exactly where the valley is, right? You can just basically, somebody can shoot you there, you fly there, right, to the valley, right? That's basically what the normal solution is. Initialization, exactly. So in gradient descent, you imagine that you are on the mountain, it's very foggy, or what you know that basically you are on a mountain, this is your feet, right? So that's where you start the initialization. And you start just look at which way it seems to be going downward compared to my current position, right? And then I move 1 or 2 feet. I repeat the same process until I get eventually down to the valley. That's exactly the difference between them. So now, in the normal equations, if capital P and capital N and small m are all small numbers, normal equation will give me the solution that I am looking for, right away. Only when I cannot really do that, then I go to the gradient descent. Okay. It's very, very important difference between the two. Any other question? So now, as an introduction to what I will talk about next time, let's look at gradient descent from a different point of view, right? Do you remember from calculus Taylor series expansion? Do you remember that? So basically, if you look in here, we have function f of x. I can approximate that function at point x equal to a, right? I take f of a plus the derivative of f at point a, divide by 1 factorial times x minus a, plus the second derivative at a, divided by 2 factorial times x minus a square, plus the third derivative, basically, and so on. You see that? Remember that from Taylor series, right? If you look carefully, remember basically our gradient descent, I always use this, especially all of us, we use this in our classical treatment of gradient descent. Imagine that this three-dimensional manifold is our data. We are at this point, like at a certain point in the mountain, I'm at this point in the green, right? I'm approximating basically my whole data as a plane, right? That's basically what we refer to as a first order approximation. Or what I'm doing actually, I'm approximating my function using these two terms. That's gradient descent, right? I'm taking the first derivative, right? So basically I'm taking the first derivative in here. That's my approximation. So now what I'm doing when I'm doing the gradient descent, I'm saying that the change, if I change my theta by this delta theta by a small amount, right? Then my cost function can be approximated using L of theta plus basically the change I have in my theta, right? Times the gradient or the change in my cost function. Look carefully at this. L of theta is what I have here off of A. The change in my theta is I have in here as x minus a. And then I have the change, the derivative of my function, which I have here. So that's my first order approximation. So really in our when I say gradient descent, it should basically, or I can replace that by saying, I'm just doing a first order approximation in this case. So we are really approximating our manifold using basically kind of a linear hyperplane, right? In the previous slides in here, I chose a line, right? For 2 dimensions, right? For a 2 dimension, my hyperplane just becomes a line. I'm approximating, right? My function. Remember, I'm here. That's all what I know. So the best I can approximate with is what? A line, right? If a 3-dimensional space that I have in my other slide, then the best I could do is what? A hyperplane, right? That's basically. So the best I could do, if I'm using first order approximation, then this is on a hyperplane, right? So now I need to move down the hyperplane. You can see the hyperplane, there is a space between the 3 dimensions. That's an error, right? What we will learn next time, is there another approximation where I can still stay with the manifold, right? So I'm not hyperplane, I want to make it as a curve, right? And that's the second order or Newton's method. Okay, so now this is a first order approximation in here, right? And basically now what I need to decide is what will be my delta theta, right? What will be the change in my theta? It happened in here, I can choose my theta to be the learning rate times my derivative of the cost function in this case. Okay, alpha is positive. This is basically in here is positive. This is gradient going taking up. I can subtract those from here, and that will basically give me still is giving me down the mountain or down to the optimal solution in here. I keep repeating that. So all what this slide is just motivation for the next subject, where what happens if I go to the second order approximation, right? So what will that mean? And what that will change in our visual model of what's really happening in here. Any question about this part? Any question? Of course, which one is faster? This one is faster because that's basically is a rough approximation. Is the first order is much quicker, right? But you can see in here there's a problem, right? I'm going basically down here, but really the function is going this way, but I'm going down here mountain, right? So there is a divergence between my steps and the behavior of my manifold, right? Again, we are trying to approximate this manifold, right? That's the manifold. That's what we are trying to approximate. Can I use the second order? Next time we'll do that. So we have only second order approximation left, and then we have evaluation, and then lasso and regression that we'll go through Wednesday, and then we'll end up finishing up the regression chapter. Any questions? For those who came late, we look at the video. We spoke about the exam in the first few minutes. If you came late, okay. We'll see you Wednesday. Thank you.